Hi everyone. Today is Thursday, April 16th, and today in science class we are going to be talking about limiting factors and carrying capacity. We're going to take a short notes entry, but it's important because you're going to need it for class on Monday. Number two, I need you to gain an understanding of how limiting factors affect populations, examples of limiting factors, and having a good idea of what carrying capacity is referring to in that concept. And lastly, there is no homework to submit for today. I've been having you submit pictures of your notes. However, I want to kind of pull back a little bit because you need to be intrinsically motivated to do this. And just know that if you don't take the notes today, it's going to impact you on Monday and actually make more work for you. So please make sure you are taking the notes because that will make your life easier in the days to come. Okay, let's get started on limiting factors and carrying capacity. Let me give you a situation here. Let's suppose we have two mice. Look, they're so cute. Two little white mice. And let's suppose they produce the typical 56 mice offspring. Okay, on average, that's what they have per year. So there are our 56 babies from mom and dad mouse there. Then each of these 56 offspring go on to have the average 56 offspring of their own. That means within the course of just 2 short years, we have created over 3,100 mice. Okay, and that's just starting with these two parents. We know there's a whole lot more parents than just two to start with. Soon, if this continued, we'd be overrun with mice on the planet. However, we know that is not the case. So why doesn't this occur? Why don't we look out the window and see seas and seas of mice surrounding us? Well, it has to do with limiting factors. A limiting factor is anything that restricts population growth. Now, we tend to hear limiting and restrict, and we think it's a negative thing. Limiting factors are excellent, wonderful things. You read about the reindeer of St. Matthew Island overpopulating and completely decimating the St. Matthew Island and also leading to their own demise. If they had had limiting factors in place, they would have had a much more stable existence. So let's go ahead and start our notes entry, limiting factors and carrying capacity. Our focus today is what are examples of limiting factors in an ecosystem. Our first definition is going to be for limiting factor. It's any abiotic or biotic, so non-living or living, factor that restricts or slows population growth. These are the wonderful checks and balances that nature has put in place for us. So nature, if you leave it alone, it tends to do just fine on its own and takes care of itself. Now, something that I want you to have an understanding of is population density. With what's happening with the coronavirus, this is probably a word you might have heard in the news lately because areas that are more densely populated are being affected more greatly. And population density, like New York has an extremely high population density, is the number of individuals per unit of area. Depending on what state you're talking about, we can have a vastly different population density. So I was kind of curious, so I looked up population density by state, and these are in people per square miles. DC has around 11,000 people on average per square mile, so very densely populated. I thought New York would have been first. I guess I was forgetting about DC. And in fact, New Jersey, New York doesn't even rate as high on the list because there are a lot of rural areas in New York as well. Pennsylvania, on average, 286 people per square mile, comparing the whole way down to Alaska here with only about one person per square mile. So much of Alaska, as you know, is uninhabited. Here's another way you can kind of picture population density. Here we have dots kind of representing the more densely populated areas. Not a surprise that the Midwest is much less densely populated than either the coast, and particularly the Northeast. Okay, so types of limiting factors. The reason I wanted you to have an idea of what population density is because we group our limiting factors into two categories. Density dependent factors, so factors that are only going to impact, populations that are fairly densely populated, okay? And these are going to be our living factors. Number one is competition. Obviously, if you have an area that's densely populated, there's not going to be enough resources usually to go around. So that's going to limit population growth. Here in the savanna, we have competition for access to water. Number two, predation. Okay, and again, this is another living factor. The more densely populated an area is, the more effective our predators are going to be able to hunt. So that's another way to keep populations in check. And then lastly, disease or parasites. This, and again, unfortunately, we're seeing this with the coronavirus. This is a picture of a chestnut tree. Most people don't even know what a chestnut tree looks like because uh, originally, you know, many hundreds of years ago, there were about 4 billion chestnut trees in the United States, in North America, I should say, until unfortunately the chestnut blight, which is a fungus that infected the chestnut trees, was introduced from Asia. So it's an invasive species and basically wiped out almost all 4 billion of the chestnut trees. I linked a TED Ed on the chestnut blight. I would highly encourage you to see it because this is what we are learning about at play in real life. So there are some scientists working to kind of restore the chestnut population. So please check that out. I think it's really good, relevant information. Okay, so those are our three density dependent or biotic factors. We also have density independent or abiotic, non living limiting factors. The first is temperature. Most organisms are kind of hardwired to thrive at a certain range of temperatures. If you exceed it, whether getting too hot, too cold, they're not going to survive. Precipitation is going to impact population growth. So, really, we're talking about access to water in some cases, and then catastrophic events. So, again, these three things are going to be the same whether they are in a densely populated area or not. The number of organisms has no impact on temperature precip or whether or not you're going to have a forest fire or hurricane. So that's why we group these as density independent factors. But all three of those things can control population growth. Okay, because we're talking about population growth, I did just want to mention human population growth because that can be concerning, especially nowadays. When we're talking about any population growth, whether it is human or any organism, there's really two kind of curves that take shape. One of these curves has limiting factors in place. One of them does not have limiting factors or little to no limiting factors. Can you guess which is which? Now, our J-shaped curve and our S-shaped curve, as we call them, if you haven't guessed, the J-shaped curve that is an exponential curve has little to no limiting factors. Because of that, we have no limits to our population growth. Human population is currently following an exponential pattern. An S-shaped curve, on the other hand, the S-shape is a logistic curve. So the population rises very steadily, but as it approaches a certain level, okay, those limiting factors are going to kick in and kind of level it off, balance it out, and prevent it from getting too high. If you haven't guessed, J-shaped curves, we don't like them. They're not stable. They're not sustainable. S-shaped curves, on the other hand, are ideal. They're as stable as you could be. This is a graph I looked up of human population growth. I also linked a video. Please watch the video. It starts off kind of slow because they're actually going to track human population growth, which, as you can see, starts slow. With the advent of or the invention of modern farming techniques, medicine, things like that, our population has skyrocketed because we basically have removed those limiting factors. So we can see we are forming a very upright J-shaped curve. Just to kind of give you another statistic that might surprise you, it took 200,000 years for human population on Earth to reach 1 billion people. However, it only took 200 years after that to reach 7 billion. So that is represented here by this extremely spiked J-curve. So check out the video. Again, I think that's understanding human population growth because we're all on the same planet is just good life knowledge. Okay, let's move on to carrying capacity. Carrying capacity is the maximum number of individuals of each species that an ecosystem could support. So kind of as the name implies. If the carrying capacity, if this maximum number of individuals is exceeded, the environment will begin to degrade. And that's why I wanted you to read about the reindeer on St. Matthew Island. They exceeded the carrying capacity, and you read about the effects of that. Limiting factors, again, they naturally keep population growth in check. Nature is an amazing thing. If we just leave it alone and let it do its own thing, it's perfectly in harmony. It's as stable as it can be. It's when we start to interfere that things kind of go wrong. Now, if you're looking at this logistic growth, the reason that this tapers off at the top is because we are approaching the carrying capacity. And as we get close to this line, this maximum number of individuals, it's going to kind of level off because that's our limiting factors kicking in and slowing this curve down. Once the number of organisms approaches the carrying capacity line, as we just said, population growth starts to level off. And it's just going to continue to kind of hover around that dotted line, around that carrying capacity line. And remember, carrying capacity, it's not going to be the same amount for two given populations. It's dependent on many things. You know, the amount of space available, the amount of nutrients available, how many organisms of each other type, you know, because we know the environment is the interconnectedness of all these organisms. So you have to really calculate it for a specific area. But as we begin to approach it, it might get exceeded. But again, those limiting factors kick in and pull those numbers back down. And it's just going to kind of dip up and down around. And this is ideal, okay? This is a sustainable population for an indefinite period of time. Okay, let's add carrying capacity into our notes. The maximum number of individuals an ecosystem can support. I do also want you to make a curve, just a very general one. So let's have our x-axis and y-axis. X, we're going to label it time. Y, we're going to label population or number of individuals. Now, as we said, as time goes on, this is more an ideal curve, okay, where limiting factors are at play. We're going to have this S shape start to form. Okay, so go ahead and put that in your notes. As we start to get towards the top of our curve, we're starting to approach this line of carrying capacity. Okay, so please make sure you label and draw this dotted line here. Whatever number this happens to be at, okay, this is going to be the maximum population, the maximum number of individuals that this environment can sustain. And as we said, over time, we're just going to kind of hover around this line. This is the most ideal kind of population growth that we're going to get. Okay. Highlight that line for me too, because you will be having some questions asked about the carrying capacity, how it's represented, etc., and the type of curve. Okay, take home points for today. Limiting factors help naturally control population growth. Limiting factors are necessary to protect ecosystem from exceeding the carrying capacity. If the carrying capacity is exceeded because we have found ways to remove limiting factors, the environment is going to be degraded, sometimes rapidly. There is no homework to submit today. As I said before, you're going to need these notes next week. I am available for office hours on Friday pause days from 9 to 12. So if you have any questions, stop in office hours or just send me an email. Have a great weekend, guys.